Hello, and welcome back to Educator.com, and welcome back to Physical Chemistry. So today we're going to start our discussion of the harmonic oscillator, and we're going to spend several lessons on it. So let's go ahead and get started. So the harmonic oscillator is pretty much exactly what you remember from classical physics. Basically, it's some system that's moving back and forth. It's oscillating just like this, back and forth, back and forth, back and forth. So we want to discuss the quantum mechanical equivalent of that. So let's start with, now, when radiation interacts with matter, it causes changes. Spell this a little bit better. It causes changes in the energy levels of the particles making up that matter. In the particles making up that matter. So the whole field of spectroscopy is a study of that, the interaction of electromagnetic radiation with matter. At different frequencies, we get different responses from the molecules or from the atoms, whatever it is that we happen to be irradiating. And so let's take a molecule like, so take a diatomic molecule. Molecule, say hydrogen fluoride. Okay, so we have that. We have this in the bond and this. So we have the H plus over here. We have the F minus over here. And this molecule, it vibrates back and forth. So this goes this way and this way, this way, and this way. Well, so this idea of a harmonic oscillator is a really, really nice model for the vibration of a diatomic molecule and the vibration, about a bond in general. So imagine a spring with two masses going like this. Well, it's pretty much the same thing. So if we can study this harmonic oscillator, extract some information from it, and then come up with a quantum mechanical version of it, it'll give us a lot of information. Now, irradiation of this molecule, excuse me, by infrared radiation causes the molecule to vibrate at different frequencies. Vibrate, oscillate. So vibrate, oscillate is going to be synonymous. Vibrate at various frequencies. In other words, it's going to change the energy level of the molecule. Okay. So this oscillation back and forth, excuse me, this oscillation back and forth is harmonic motion. Harmonic motion. And harmonic motion just refers basically to sines and cosines. Because you remember sine and cosine curves, they repeat themselves. They're harmonic. Harmonic means periodic, repeating, just back and forth, back and forth, back and forth. That's all harmonic means. So now we want to examine this harmonic behavior. And we want to examine the quantum mechanical harmonic oscillator. But we're going to begin with the classical harmonic oscillator and then move on to the quantum mechanical harmonic oscillator. We'll get a lot of information by actually studying the classical harmonic oscillator. So we wish to examine the QM harmonic oscillator. And we begin with the classical harmonic oscillator. Okay. So let's go ahead and, let me see, let's go ahead and start on a new page. So consider the following system. So we have basically a setup like this, and this is a wall. So we're going to fix one end, and we're going to have a spring with a mass on it, and it's going to be just a spring in its normal, unstretched, uncompressed string, what we call the equilibrium length of the spring. So we're going to call that S0. So there's a mass. It has mass M. Okay, so S0 is the distance of the undisturbed spring. And again, we're making it simple for ourselves at first by holding one end fixed and just having one mass oscillate back and forth. So it's going to oscillate around some equilibrium position. That's how it is with all of science. We start with the simplest case, and then we move up in degrees of complication until we arrive at something which matches what we want, our real world. It's always like that. Start with the simplest case and move your case and move forward from there. Okay, now we can, of course, we can stretch the spring or compress the spring a distance S. So we can stretch or compress the spring a distance S. So let's go ahead and take a look at some of those. Now, if we stretch the spring, so we've got so here we stretched it, and now this distance is S. Or we can go ahead and compress it. We've pushed the spring in. Let me make it a little bit more. There we go. So we've taken it and we've actually pushed it in. So now this is the distance S. Okay? Now, no gravitation is acting on this, no gravitational force. So the only force that's acting on this mass is the spring. I pull the spring this way, the spring is going to want to pull it back that way. I push the spring in, the spring is going to want to push back the other direction. Okay, no gravitational force acts on the mass. So far so good. Spring. The spring force is the only force acting on the mass. Okay, now Hooke's law, you remember hopefully, or you remember having heard from your physics course. Okay, the force acting on a mass attached to a restoring medium. In this particular case, the restoring medium is the spring. It could be something else. It could be a rubber band. Anything that will, as you pull it, tries to pull it back. As you push it, it tries to push it back. Restores it back to its equilibrium position. So the force acting on a mass attached to a restoring medium is directly proportional to the displacement. And the displacement is the extent to which I actually pulled it away from its equilibrium position. So from here to here, that's the displacement right there. That's the displacement from its equilibrium position. It's the S minus the S0. Is directly proportional to the displacement. So that is Hooke's law. And the mathematical statement is the force is actually equal to minus K times S minus S0. So if I've stretched it, S is bigger than S0, right? The stretched is bigger than the equilibrium position, so the S minus S0 is positive. The force, we put a negative sign in front of it because now the force is actually pulling the mass back that way. If I push it in, now our S is smaller than our S0. This ends up being negative, and this negative sign in front actually makes the force go in the positive direction. So it's opposite. That's it. I pull this way, the force wants to pull it back that way. I push this way, the force wants to push it back that way. That's why the negative sign is there. So this is Hooke's law. Okay. So now K is the force constant. K, that is called the force constant or the spring constant. Force constant or spring constant. Okay, now a large K means you have a very stiff spring. And a small K means you have a very loose spring, very, very easy to push and pull. That's it. Okay, so we have F is equal to minus K times S minus S0. And again, let's go ahead and draw this out. So this is the equilibrium position, okay, of the spring. If I had it stretched out, this distance would be my displacement. This is my S minus S0. And the force, if I stretch it, the force is going to want to pull it back that way. And of course the compressed, I've pushed it in from its equilibrium position, so this is the equilibrium position. Now we have, it's right there. That's the S. That's the S0. S minus S0, that's this displacement right here, and the force is going to be pushing that way, trying to push it back to its equilibrium. The restoring force, the restoring medium. Okay, so we have this. Well, we also know from Newton's second law that force equals the mass times the acceleration, and it equals the mass times, well, the acceleration is the second derivative of the displacement. So the displacement is S. The first derivative of that is going to be the velocity. The second derivative is going to be the acceleration. So we can write d squared s dt squared. Now, let's let x be the net displacement. And net displacement means this distance, the actual distance I've pulled or pushed away from the equilibrium position. So this is x, and this is x. Net displacement. In other words, it is s minus s0. So mathematically, we're going to let x equal s minus s0 because we're ultimately concerned with, so s0 is the initial, s is the final. The difference between them is the displacement. Okay, so x equals s minus s0, which means that s equals x plus s0. So now, f and f, I'm going to set them equal to each other. So I have m d squared s dt squared equals minus k times s minus s0. Well, we said that x is equal to s minus s0, so I'm going to put x in for here. And the d squared of s dt squared, well, I'm going to take the derivative of this. So ds dt equals dx dt. This is a constant. It's just the equilibrium position, so the derivative is just 0. And then, of course, if I differentiate twice, it's just going to be d squared s over dt squared equals d squared x over dt squared. That's it. Nothing strange going on here. So when I put this in for this, I get m d squared x dt squared equals minus kx, or more appropriately, m d squared x dt squared plus kx is equal to 0. This is the differential equation for a harmonic oscillator. This is the equation that we solve in order to find the function x of t. Okay, When we find x of t, what that tells us that at any time t, it's going to tell us exactly how far this mass is from the equilibrium position. Where is it? That's what we're doing. So this is the differential equation we solve. Now, the general solution of this equation, I'm not going to go through the actual solution of it. We'll just go ahead and give it to you here. So the general solution of this differential equation is, so a little bit more room here, x of t equals c1 cosine of omega t plus c2 times the sine of omega t, where omega is actually equal to the force constant divided by the mass, the square root of it, or to the 1/2 power. So instead of putting this, we just use the omega. Now, x of t, as we just said, x of t tells me how far the mass is from the equilibrium position. At any time t. That's it. Okay? So you have this mass equilibrium position. If I pull it and let it go, it's going to just bounce back and forth, back and forth, back and forth, oscillate. This equation tells me where, how far from the equilibrium position it is. X at time t. That's it. That's all I've done. Okay, so now let's go ahead and take this mass and that's the equilibrium position. So what I've done is I've actually pulled it, I've stretched it out, and now I'm going to let it go. When I let it go, it's going to oscillate back and forth, back and forth, back and forth. Okay, so now let's actually work this out. So this is the general solution. Okay, we want to find some specific cases. Now, the initial position, let me go to blue here. So, initial position, in other words, x at time 0 is equal to a. A is the distance that I've pulled it. Okay? I've pulled it a distance a. Let's go ahead and call that a. The initial velocity, well, the velocity is the first derivative, so x prime at t equals 0. Well, it's 0. I haven't let it go. It's when I let it go, that's when it starts. So the initial velocity is actually 0. Now we have c1 cosine omega t so we have our equation, which is x of t equals c1 times cosine of omega t plus c2 times the sine of omega t. So the x of 0 is equal to c1 times the cosine of 0, when I put 0 in for t, here and here, plus c2 times the sine of 0, and we know that x of 0 is equal to a. Well, the sine of 0 is 0, so that term goes to 0. Cosine of 0 is 1, therefore c1 is equal to a. So we found the c1. We found that coefficient. Okay, now let's take x prime. Well, let me rewrite the equation up here. So x of t equals c1 times the cosine of omega t plus t to the sine of omega t. Well, x prime of t, that's going to equal minus omega c1 times the sine of omega t plus omega c2 times the cosine of omega t. Well, x prime of 0 equals minus WC1 times the sine of 0 plus omega C2 times the cosine of 0. And we said that that actually equals 0. Well, this is 0. This becomes C2W equals 0. Well, W is not equal 0, which means that C2 equals 0. So now we went ahead and found C2. So we have x of t is actually equal to A times the cosine of omega t. We found a specific solution under the circumstance of me pulling it and letting it go. Okay, the period. This is harmonic motion. You know what a cosine function looks like. It starts up at, in this particular case, A is the amplitude, and it goes like this. Oscillates back and forth. This is harmonic motion. It's always going to be in terms of sine and cosine. The period of this oscillation is equal to 2 pi divided by the omega. Okay? The frequency of the oscillation is equal to the omega over 2 pi. It's the reciprocal of the period. And it's in cycles per second. Cycles per second, otherwise known as a hertz. We often don't include the cycles, we just put second, usually like this, inverse second. Okay, so this is frequency. Okay, now let's take omega over 2 pi cycles per second. Let's multiply by how many radians are there in a cycle? Well, if you do one circle, it's 2 pi radians. So it's 2 pi radians per cycle. Okay? The 2 pi and the 2 pi cancel. I'm left with radians per second. So omega, the unit is radians per second. This is the angular velocity. So we have our period, we have our frequency, we have our angular velocity, which is omega, and A is called the amplitude. A is the amplitude of the oscillation. It's the largest value that the amplitude can actually have. If I stretch something A, when it goes the other direction, it can only compress the spring a distance A, maximum, and then it's just going to go back and forth, A minus A minus A minus A, something like that. So A is the amplitude of the oscillation. Okay, so all of this information is extractable from this. Amplitude, angular velocity. Angular velocity divided by 2 pi gives you the frequency. Take the reciprocal of the frequency, it gives you the period. Or you can just take 2 pi over the angular velocity, that'll give you the period. All of this information comes from that. Okay. Now, recall from physics. Let me go back to blue here. So recall from physics that a force is equal to minus the derivative of the potential energy. So dV equals minus f of x dx. So if I want the potential energy, it equals minus the integral of the f of x dx. I just integrate that equation. Well, here, our f of x is equal to minus kx. That's Hooke's law. The force acting on the mass is directly proportional to the extent to which I actually pull that mass away from its equilibrium position. So, our potential energy is equal to minus the integral of minus kx dx, which means it's equal to 1/2 kx squared plus some constant. We can set c equal to 0. It's just the 0-point energy. Okay? So we can go ahead and set that to 0. So what we get is that the potential energy stored when I stretch the spring or compress the spring is equal to 1/2 kx squared. Very, very important. That's the potential energy of a mass spring system. Okay. So we have our v of x is equal to 1/2 kx squared. That's nice. Well, our kinetic energy, we know the kinetic energy is equal to 1/2 the mass times the velocity squared. Well, velocity is just the derivative of the x is dx dt, so I'm just going to go ahead and call it x prime squared. Okay. Well, x of t, we know that x of t is a times the cosine of omega t. When we take the first derivative, which is going to be the velocity, it's going to end up being negative omega a sine of omega t. So we have, let's go ahead and we put those back in. This is x of t, x prime of t. We're going to put these into here. So our potential energy is actually equal to 1/2 k times a, the cosine of omega t squared, which is going to equal 1/2 k a squared cosine squared omega t. This is our potential energy of our classical harmonic oscillator. Now let's go ahead and calculate the kinetic energy. The kinetic energy is equal to 1/2 the mass times the derivative squared. The derivative squared was minus a omega cosine, no, not cosine, sine, because we took the derivative, sine omega t squared. Excuse me. So we end up with, the negative squared cancels out, so we end up with 1/2 m a squared, yes, o squared sine squared omega t. This is our kinetic energy of the harmonic oscillator. Well, the total energy of the system, we know, is equal to the kinetic energy plus the potential energy. So our total energy, we just add them up. Just 1/2 m a squared cosine squared omega t plus 1/2 m omega squared a squared, sorry, I just switched the omega squared and a squared. I don't know. Sine squared omega t. So that's an expression for the total energy of the harmonic oscillator. When I plot these, this is what I get. Equilibrium position, that's A. This is minus A. A, equilibrium, minus A. It's going to oscillate back and forth like this. Here's what it looks like. There, there, there. Hope I can draw it well. I'm not the best drawer in the world. That's that. And of course we have this up here. Let me do this one in red. There we go. And let me go ahead and go to black. This right here, this is the potential energy curve. And this right here, the red, that's the kinetic energy curve. Notice what's going on. I pull the thing to A. All of the energy is potential. There's no velocity yet. I haven't let go. Zero kinetic energy. I release it. It starts, all that potential energy starts to go to kinetic. At some point they meet where the kinetic and the potential are equal. As it passes through the equilibrium position, because it's actually at the equilibrium position, x is 0. Therefore, the potential energy is 0. However, the kinetic energy is at its maximum. And then it starts to slow down. As it passes through the equilibrium position, it starts to go towards the negative. It's going to start to slow down. So the kinetic energy is going to drop down to 0, and the potential energy is going to rise to its maximum. Back and forth, back and forth. Notice the sum of the energies is actually constant. So the kinetic and potential energy, they switch off. but the total energy of the system is constant. And we'll go ahead and do it algebraically right now so you can see. So let's go ahead and write this out. Let's go ahead and write it in blue. At maximum displacement, the mass has stopped, which implies that the kinetic energy is equal to 0. V is at a maximum. Here and here. Okay. As the mass passes through the equilibrium position, now the potential energy is equal to 0, and K is a max. Here and here. Potential is 0. Kinetic energy is at a max. At the ends, it's the potential energy that's at a max. The kinetic energy is at 0. And they switch off. Okay? In between, we have some of both. That's it. Now, let's go ahead and... So we have our energy is equal to 1/2 m a squared cosine squared omega t. Did I get that? Wait, did I squared omega t? I think did I get my equations right here? I'm always messing up my sines and cosines. Kinetic plus potential. Actually, you know what? Let me just write it the way that I have it written here. Yeah, it's probably better. I've got, let's see, okay, wait a minute. Now let's make sure I have this right. I want to sort of maintain the order that I've actually used in here. Potential is going to be the K, and it's going to be OK. Squared O squared. Yes, that's right. Sorry about that. So we've got 1/2 mass A squared omega squared sine squared omega t plus 1/2 K A squared cosine omega cosine squared omega t. So kinetic energy plus potential energy. Now recall that that is equal to K over m to the 1/2. So omega squared is equal to K over m. I can go ahead and put that into there. Therefore, I have my total energy is equal to 1/2 m a squared K over m sine squared omega t plus 1/2 K a squared cosine squared omega t. The m cancels the m. I go ahead and I combine terms and factor out. I have 1/2 a squared k, 1/2 a squared k. So I have 1/2 a squared times k times sine squared omega t plus cosine squared omega t. And you remember from trigonometry that sine squared plus cosine squared is equal to 1. Therefore, my energy, my total energy is 1/2 a squared times k. Total energy of the harmonic oscillator. This is a constant. A is the amplitude. It's a constant. K is a constant. So this is an algebraic representation of the fact that the energy of a harmonic oscillator is constant. It oscillates back and forth between the potential and the kinetic. They trade off, and one of them is maximized, the other is minimized. The one of them is minimized, the other is maximized, but it is a constant. Perfect. Okay. So let's see. So we have now a system where the total energy G is conserved is called, appropriately, a conservative system. The harmonic oscillator that we've described is a conservative system. Energy is a constant. It's transferred between kinetic and potential, but it is a constant. It doesn't go away. Energy is conserved. It isn't lost to anything. Okay, thank you so much for joining us here at Educator.com. We'll see you next time for a continuation of a discussion of the harmonic oscillator. Take care. Bye-bye.